In what senses, and there are a lot, so we'll get to them, but in what major senses did the universe appear to have been fine-tuned for us? And maybe, just to phrase this differently so that it takes out the question of who does the fine-tuning, which I think it immediately comes from the way the question tends to be phrased. What sorts of delicate aspects of this universe's physics make life like us possible?
Well, I think the starting point has to be remembering that, in our laws of physics, we have these numbers that we need to basically run the laws of physics. So if Newton wrote out his formula for gravity, GMM over R squared, which everybody learns in school, but you can't do anything with that equation until you work out what the G in that equation is. And the only way you can find that is by asking nature. So the famous Cavendish experiment for measuring the gravitational constant. So physics is filled with these constants that have specific values. And there's nothing in our theories that tell us why these numbers are the way they are. And, some of them, the speed of light, the gravitational constant, the fine structure constant, all of these numbers all the way through physics. Physics is sterile until you've nailed down those numbers. So we can play this game immediately as physicists. We can start to ask ourselves, how would the universe have been different if these numbers had been different? Would it all have just played out somewhat the same and things would be slightly different? And so we can look at things like what happens if you mess with, say, the mass of the electron, or the mass of the quarks, which make up the protons and the neutrons, or the strength of gravity, or electromagnetism, etc. And it's one of those things where there's almost a butterfly effect, in the sense that the changes that you make to the small scale universe propagate to large effects when you look at the universe as a whole. So there's a couple of the ones that I think are very telling. Of course, the mass of the electron, right? The electron is small compared to protons and neutrons in atoms. And so we have this picture of the atom, and you've got your nucleus, you've got an electron going around the outside, and the electrons are the things that talk with other atoms, and that's all kind of fine. But if you start to wind up the mass of the electron, right? So it's like 1/2000th the mass of the proton. If you start to wind that up, okay, and you make the electron more massive, then instead of there just being a nucleus with this electron whizzing around outside, there's now a tug of war going on between the two of these. And that means is that outer part of the electron, where the electrons live, when they talk to other atoms, instead of there being just like this, the way chemistry works, like, an electron will hop over here, etc. They are really basically thumping against each other. And that has a big implication for solid material, right? The stuff which you need for planets and planetary surfaces and all this kind of stuff. You can start to disrupt that by winding up the mass of the electron and making it kind of heavy. Now, you have to go quite a long way with the electron, right, to make it massive enough to really be, something that's very disruptive. But the change is actually kind of small compared to the potential range that an electron mass could be. And it's very hard to judge what that could be. But of course, at the bottom end, electrons could be massless. They have no mass at all. And where's the upper end? And if you talk to the quantum people, the string theorists, etc., they'll tell you that's the Planck mass. And the Planck mass is huge, right? It's a grain of dust, which is much, much bigger than the mass of the electron. So we can adjust the mass of the electron, and if it was up at the higher scale, we would clearly be in a very different universe. And we play the same games with quarks inside protons and neutrons. And one of the things that we have in the universe, of course, is that the proton is ever so slightly, only like fractions of percent, less massive than the neutron, which means that neutrons decay into protons and not the other way around. So we end up with these nuclei that we have for atoms. But if it was the other way, if we adjusted the masses of the up and down quarks, we could make the neutron slightly less massive than the proton, which would mean that protons would decay into neutrons. And that would mean that we would have a universe full of neutrons, and neutrons are useless. right? Electrons don't join onto neutrons to form atoms, right? So you just have this sea of particles that don't join together. They're neutral. They just all sit there. So what you can quickly do, and this is what we find when we look at all of these different experiments, thought experiments, is that you rob the universe of the potential for complexity. Okay, so a universe filled with neutrons is a boring universe where there are no atoms, there's no solid material, there's no stars. And clearly in that kind of universe, there's going to be no life. And I said, if you play this game, you adjust all the constants, and with the quark masses, it's only a little bit, then you rapidly end up with dead and sterile universes, either universes which are effectively empty, so there's nothing in there at all, or universes filled with things like neutrons where, the thought of a periodic table, that's just a dream. You can't do anything in that kind of universe. So yeah, it's easy to wipe out complexity and therefore the possibility or the prospects for life in those universes.
Well, this is exactly the game I want to play because, like I said earlier, it's a great opportunity to talk about some of these other numbers beyond the electron to get a sense of some of the big topics in theoretical physics and astronomy. But before we go into more particularities and see how our universe might have been totally unrecognizable or recognizable, is what you just said a few minutes ago, that as we tinker with these numbers, we might rob the universe of the potential for complexity. Is that the key sort of dimension of fine-tuning that we're figuring out? How much can things be messed around with and maintain the complexity that can result in life?
Absolutely. So one of the biggest problems with the anthropic principle is the anthropic part of it, right? Because people think the argument is based upon humans, people, but it's not. It's about the ability for the universe to host complexity. We are a result of the complexity in this universe, in the sense that we have a periodic table with 92 natural elements. Those elements can combine together to give you molecules. Those molecules can process information, right? And we are molecular machines. That's what we are. We are essentially the periodic table written in large form in the universe. So it is about that complexity, because at some level, that's without getting into with the definition of what life is and what life could be, the notion of having a complexity in your environment for information process and energy processing is one of the key requirements that we're looking at. So yeah, it's like the base level that we start with is, can this universe host complexity?